Alright, welcome back. Now, I'm going to apologize right off the bat if I make more mistakes than usual in this lecture. I got stung by a wasp today, and it turns out that since the last time I got stung, I have developed an allergy to wasp stings. So I got to spend some time at the hospital and get some medications there, and then pick some more up at the pharmacy, and so on. Which means I couldn't drive down to Charleston for tonight's class, but I'm not going to let free time go to waste, so I'm going to go ahead and work on this lecture. But I am a little out of it, and I'm going to be doing some math, so that at least is my excuse. I may end up reworking this lecture at a later date. Now, on to Le Chatelier's principle. Le Chatelier's principle says that if you have a system at equilibrium, and you disturb that equilibrium, either you change the amount of reactants, or a reactant, or a product, or if you change the pressure, if there are gaseous reactants or products, or if you change the temperature. Whatever change you make, the system will try to undo. Okay? The equilibrium will shift in such a way that whatever change you've made will be minimized. Or, in other words, every equilibrium out there is the grumpy cat. Okay, let's take a look at some examples. Now, first here we have vinegar, or acetic acid, HC2H3O2. Oh, darn it. These should all be aqueous. The vinegar on the left, the H plus on the right, and the acetate on the right. They should all be aqueous. And you have a KEQ, an equilibrium constant, of 1.8 times 10 to the negative fifth. So, let's say you have a 1 molar solution of acetic acid. Okay, first we'll let that reach equilibrium. Then we will remove all of the acetate ion. There are a couple of ways to do that. We'll worry about that when we get there. First, let's find out what the equilibrium concentrations are. Now, I know I haven't shown you how to calculate these yet, but that's okay. It's better to have an idea of which way the system is going to move before you try to find out exactly where it's going to move to. That way you can check the numbers that actually come out against your qualitative understanding, your intuition about which way the thing should go. But rest assured, I am doing the math behind the scenes on this. So you dump acetic acid into water to make a 1 molar solution. Let it come to equilibrium. You're going to end up with 1 molar of acetic acid. 1 molar is such a high concentration, and acetic acid has such a low equilibrium constant that it's not exactly 1 molar, but it's so close that we can't really see the difference. So you're also going to have 0.0042 molar H plus floating around in solution, and 0.0042 molar acetate ion floating around in solution. It's a 1-to-1-to-1 relationship, so you're going to have the same concentrations of H plus and acetate in this step. Now, let's go ahead and disturb this equilibrium by removing the acetate. There are a lot of different ways you can do that. For example, you could throw silver nitrate in there. If you recall your solubility rules from way back in the day, silver nitrate is going to be perfectly soluble in water because nitrate is always soluble. But silver generally is not. And in this case, it will react with the acetate and come out of solution. It'll precipitate out of solution. So we dump in a sufficient quantity of silver, you can pull out all of the acetate. So what happens, for those of you who like pictures, is that you start off with a whole lot of of acetic acid and a small quantities of H plus and acetate. And then you dump in, the silver nitrate, and that pulls the acetate out of solution. leaving you with your disturbed equilibrium with acetic acid, H plus, and nothing. We've pulled out all of the acetate anion. In other words, we just dug a hole on the product side. Now, Le Chatelier's principle is going to come in and try to fill it, which means it's going to come to a new equilibrium. It's going to turn some more acetic acid into some more H plus and some more acetate. It can't just make one of the products. That's not how it works. It has to make both. Matter's neither created nor destroyed. If you want to get acetate ion out of vinegar, you also have to make some H plus. So when you come to a new equilibrium, you're going to have still really close to 1 molar acetic acid. And you're also going to have 0.0068 molar H plus, because you also made H plus. And you're going to have 0.0026 molar acetic acid. It's not at the same equilibrium, and you still have less acetic acid than you started with. Less acetate anion than you started with. But you haven't completely eliminated it. Le Chatelier's principle has successfully filled in the hole that you dug a little bit, not entirely. And at this point, I feel the need to stress that this is not how it actually happens. It's not a step-by-step process. Okay, the removal of the acetate ion and the production of new acetate ion happens simultaneously. But what matter exists in what forms, that's a state function, so we can pretend. We can separate it out in discrete steps like this, and it still works. But, and. Now, that said, let's go ahead and move on to our next example. Dissolved carbonic acid. Dissolved. Damn it. It's not dissolved. I should have put the phases on here when I originally wrote it. It is solid calcium carbonate. That's solid limestone. Dissolving in water to form minute quantities of positive calcium ion, calcium 2 plus, cation, and the anion carbonate, CO3 2 minus. And as you can see, the equilibrium constant for the solvation and ionization of calcium carbonate is very low, 2.8 times 10 to the negative 9. That's 8 zeros to 8. Okay, it's a very, very small number. But as we'll see, just because limestone is almost entirely insoluble doesn't mean it is in fact entirely insoluble. But it is mostly insoluble. That's why we have most of our, a lot, I should say, of our aquifers, of our solid ground is made up of limestone. It forms a very good, basically giant stone sponge for water to sit in and wait for us to drink it. But it's not perfectly insoluble. If you've ever been to some nice caverns, I think the La Brea caverns are the ones closest to here, you'll see stalagmites and stalactites that have been formed by minute quantities of calcium carbonate being dissolved in water and then being left behind as the water evaporates while dripping from the ceiling onto the ground. Anywho, here is the reaction written again, this time with the double arrow as appropriate and with the states of matter as it should be, or the phases. Solid calcium carbonate going to form aqueous calcium and aqueous carbonate. But here's the thing. Calcium carbonate becomes even more soluble in water with the addition of any sort of acid. Because what happens is the H plus will react with the carbonate to produce, in an equilibrium reaction, bicarbonate. Yeah, you might remember that from talks about baking soda. Sodium bicarbonate is baking soda, NaHCO3. But then it can happen again. The bicarbonate can react with another H plus to form carbonic acid, H2CO3, which you'll recognize from soda pop. But then a different equilibrium reaction can take place because the sodium bicarbonate, or sorry, not sodium bicarbonate, but the carbonic acid can undergo an equilibrium reaction to produce liquid water and dissolved carbon dioxide. So you have this series of reactions, all of which involve one another. It's a big, complex mess. But we can actually, without doing any math, the math on this problem would be hideously awful. Not even I would assign that as either a homework problem or a test problem. But we can qualitatively see the results by looking at Le Chatelier's principle. Okay, now try to follow along. First, calcium carbonate dissolves, producing calcium and carbonate. Then H plus reacts with carbonate to produce HCO3 minus. That forces Le Chatelier's principle, the calcium carbonate, to dissolve more, to produce more calcium and more carbonate. Then the HCO3 minus, the bicarbonate, reacts with H plus to produce H2CO3, which pulls HCO3 out of solution, which pulls more carbonate out of solution, which pulls more calcium carbonate into solution, producing more calcium and more CO3. Then the H2CO3 breaks apart into H2O and CO2, which pulls out the H2CO3, which pulls out more HCO3 minus, which pulls out more CO3 minus, which pulls more CaCO3 into solution, producing even more calcium and even more carbonate. And then, depending upon the atmospheric conditions, the carbonate that's dissolved in the water can leave the water as a gas, which does the whole thing one more time. It pulls H2CO3, which pulls HCO3 1 minus, which pulls CO3 2 minus, which pulls more calcium carbonate into solution. Which means that if the water going into the ground is even a little bit acidic, it's going to dissolve a lot of that limestone. The result is going to be a lot of calcium ions and what's known as hard water. Hard water isn't too awful in and of itself, except that, yes, it is. Hard water is the reason you get soap scum. It's the reason your shower is so hard to clean. It's the reason why you get water spots and films on the glasses that you put through the dishwasher. And it's the reason that it's so hard to wash your damn hair. Not me, I don't have hair, but if I did. Because the calcium ions in hard water will react with your soap. Your soap is made up of ions. That's why it's dissolved. And it will pull those soap ions out of solution and make them more or less useless. So if your water is very, very hard, then your soap probably won't lather all that well. It won't feel like it's really soapy. Because it'll have to react with all the calcium floating around in your water before it can actually start to get you clean. A lot of modern soaps add what are known as softening agents in order to help you overcome that problem. So some soaps will feel slimier to you than others. Those slimy soaps are ones that have softening agents added. That's a good thing. You want them to have those softening agents in there because it makes your soap more powerful and more effective, so that your shower doesn't get quite so scummy and your glasses don't get quite so scummy, and so that your hair doesn't get quite so scummy. If you want that sleek, shiny hair like they show in the commercials, then get somebody to do your hair for you. If you just want normal, sleek, shiny hair, get good soap, or get an ion column to soften the water before it comes into your house. And I recommend that in any case because hard water can damage a water heater. Which is because, and this is a great way to tie it back in, hot water has lower solubility for gases, which means that CO2 is going to come out of solution, which, boom, 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 is going to pull a lot of calcium out of solution. So yeah, You definitely don't want hard water going through a water heater. It builds up what's known as lime scale, and eventually just completely clogs your heater and ruins it. All right. In any event, that's been about 15 minutes, so I'm going to go ahead and call it a day with Le Chatelier's principle. And when we come back, we will start looking at the math, I think.